Have you ever found yourself just staring at your screen, maybe a little frustrated? You're looking for something specific online. You type in what feels like a perfectly clear question.
Oh, absolutely. We've all been there.
And the search results that come back, they don't quite hit the mark, do they? It's like the system hears the words, maybe, but doesn't really get the intention, you know, the nuance of what you really mean.
Exactly. You end up with this sort of jumble of keywords, not the actual insightful answer you were hoping for. It's like talking to someone who only understands nouns but not verbs or context.
Right. And for years, that's kind of how traditional search engines worked, based on that simple principle, matching keywords.
Yeah, if you typed car, it went looking for car. If you typed automobile, well, it looked for automobile. The system basically expected you to speak its language, to use the exact terms it had indexed.
Instead of it understanding the natural, often kind of messy ways we actually express ourselves.
Which really highlights that fundamental challenge, doesn't it? How do we actually teach computers to, well, truly comprehend human language?
That's the absolute core question, and it's exactly what we're diving into today. Imagine, just for a second, a search engine, or really any digital assistant, that doesn't just, like, process the individual words you type,
Uh-huh.
but genuinely interprets the intent behind your query. It understands the broader context you're operating in.
That's the promise, isn't it? The extraordinary promise of semantic search.
It really is.
Right.
And in this deep dive, we're going to try and unravel how that promise is actually being transformed into reality.
And what's so fascinating here, I think, is the shift we're seeing. We're moving beyond just simple pattern matching, looking for identical strings of text,
Yeah, the old way.
towards something more like digital understanding, where systems learn the subtle complexities, the relationships inherent in our language. It's about building systems that can almost anticipate your thought, not just, echo back your words.
So our mission today is to unpack exactly how this is done. We're exploring this really fascinating world of semantic search, the tech that goes beyond those old keyword limits.
And our main guide for this journey is going to be a really detailed exploration we found, semantic similarity with FAISS Colab. It lays out the foundations, the crucial technical bits, and some pretty compelling practical applications of this, well, groundbreaking approach to getting information.
Okay, great. So by the end of this deep dive, hopefully you won't just know what semantic search is.
Right.
You'll also get a real feel for the kind of ingenious engineering that lets these systems truly comprehend language.
It's like offering you a shortcut, really, to being deeply well-informed on this cutting-edge topic. So you can grasp not just the what, but the crucial why behind this big technological leap.
Yeah, demystifying the magic a bit.
Exactly, appreciating the intelligence that's actually baked into these systems.
Okay, so let's start by zeroing in on the specific problem semantic search was basically built to solve. Think back to those frustrating experiences with older conventional search engines.
Right.
Let's say you're trying to find information about, I don't know, medical professionals. If you typed in doctor, you'd mostly get results with that exact word.
Yep, just doctor, doctor, doctor.
But what if the information you actually needed used terms like physician, or maybe medical practitioner, or even just GP?
Traditional keyword search just wouldn't connect those dots easily. It's limited to those exact or maybe very close word matches.
So you'd find yourself playing that game, right? Like synonym roulette, trying different words just to hopefully stumble across what you're actually looking for.
It's true. And that limitation really comes from a fundamental lack of, well, genuine understanding by the search system. Think about a word that's really ambiguous, like Jaguar.
Oh, good one. Yeah.
If you just searched for Jaguar, what would you get? Info on the car.
Or the big cat.
Or maybe even that old Apple operating system. A traditional search engine, because it doesn't grasp the context of your search, would probably just give you a mixed bag.
Or maybe prioritize based on whatever's most popular, which might not be what you wanted at all.
Exactly. It really struggles to comprehend the meaning behind the words, and that often leads to irrelevant results, or just too many results, especially if your query is a bit nuanced or like Jaguar ambiguous.
Okay, so let's define it then. What is semantic search at its core?
Our source puts it quite nicely, actually. It says semantic search transcends the limitations of traditional keyword searches by understanding the context and nuances of language in user queries.
That's a great summary. It really is a fundamental paradigm shift in how we interact with information.
So it's really about interpreting intent.
At its heart, yes. It enhances the search experience by interpreting the intent and contextual meaning behind your search queries. It's actively trying to figure out what you really want to know.
Even if your phrasing isn't perfect. Precisely. So if you type something like, best place for authentic Italian food near me tonight,
Okay.
it doesn't just hunt for the words Italian and food. It intelligently infers you're looking for a restaurant, probably nearby, geographically speaking, probably open right now, and likely one with good reviews or high ratings.
Right. That goes way beyond just matching those specific words.
It's understanding the whole sort of conceptual landscape of your request, what you need.
And a big part of that understanding comes from its ability to analyze relationships between words, doesn't it?
Absolutely. The source says it delivers more accurate and relevant search results by analyzing the relationships between words and phrases within the search context.
So it intrinsically knows that doctor and physician are linked conceptually.
Or that car and automobile mean the same thing in most contexts.
Okay.
This ability builds a much richer, sort of more interconnected knowledge base inside the system, which lets it retrieve information that older search methods would just completely miss.
And it keeps learning too, right? Adapting.
That's right. The intelligence just keeps growing. Over time, it actually refines the results for better user satisfaction by adapting to your individual behavior and preferences.
Ah, so personalization.
Exactly.
Hmm.
If you often click on results about, say, electric vehicles when you search for car, a semantic search engine will start to subtly prioritize those kinds of results for you in the future.
Making the whole experience feel more intuitive and tailored over time.
Yeah, it becomes much smoother.
So how does this smart assistant actually pull this off? The source gives a pretty good simplified breakdown. Step one is getting the gist.
Right.
Instead of just spotting keywords in isolation, the engine digs deeper to find the real meaning of your whole query.
It's like having a conversation with someone who actually listens to your entire sentence, you know?
Yeah.
Grasping the full picture, not just latching onto one or two words.
So if I ask, I need to find a way to get from where I am to the nearest train station, it gets that I'm asking for directions or transport options.
Exactly. Not just looking for the words location and train station separately. It understands the underlying task.
Yeah, that's step one. And step two is making connections.
This is where it intelligently understands how different words and concepts relate. Like we said, knowing doctor and physician are the same profession.
Or car and automobile.
Right. It's building this sophisticated network of associated ideas. So if a document uses the word auto and your query uses car, the engine sees that conceptual link.
Ensuring a much more comprehensive search.
It's like it's building this huge mental map almost where ideas are linked by meaning, not just by having the same letters.
And then the final step, after getting the gist and making connections, is pick the best.
I love the analogy the source uses here. A librarian who knows every book in the library.
That's good.
This intelligent system sorts through this vast ocean of information to pick out exactly what matches your query best, always considering your probable meaning, your intent.
So it's a conceptual match, not just word for word.
Precise.
So what does this really mean for you, the listener, in your, everyday life?
Well, fundamentally, it means a lot less frustration and a huge increase in precision.
You get to the information you actually need faster.
Much, much faster. It really feels like your search engine has finally learned to speak your language. It anticipates your needs rather than just reacting literally to the words you type.
Think about the practical uses, like researching complex stuff for work, maybe, where jargon might be inconsistent.
Or finding obscure historical documents, perhaps. Or even just looking up a recipe where ingredients have multiple common names, you know?
Yeah, semantic search promises to make all that much more effortless. You don't have to keep struggling to find the right keywords anymore.
Because the search engine is doing that heavy lifting of understanding what you actually mean.
And if you think bigger picture.
Well, this shift, this profound move from keywords to meaning-based understanding, it's foundational for so many other AI advancements we're seeing.
Like chatbots.
Exactly. Think how far chatbots have come, offering genuinely helpful, coherent conversations, or recommendation engines suggesting movies or music you actually like.
Or assistants like Siri or Alexa understanding complex commands.
All of that hinges on this ability for systems to truly comprehend human communication, to move beyond just parsing text to really grasping linguistic meaning. It's genuinely reshaping how machines interact with our whole world of language.
Okay, so we've talked about the impact of semantic search, how it works conceptually. Now let's pull back the curtain a bit more.
Let's get into the technical weeds a little.
Just a little. Let's talk about the actual engine powering this. It involves some numbers, some math concepts, but I promise this is where the real ingenuity shines through. we need to talk about vectors.
Right, vectors. In this context, a vector is essentially just a list of numbers that the computer uses to represent the meaning of words or sentences.
So it's the computer's way of quantifying meaning, turning something abstract like language into something it can process.
Exactly. It's a sophisticated way to do that.
And to kind of visualize this, you can imagine each word or phrase or even a whole sentence as a point in space.
Not physical space, obviously.
No. More like a high-dimensional conceptual space where meanings live. And the core idea is actually pretty intuitive. The closer two points are in this semantic space, the more similar their meanings.
Okay, so words like king and queen would be plotted really close together.
Yeah, and maybe royalty would be nearby too. But all of those would be pretty far away from, say, banana.
Right, got it. That spatial relationship is how the computer represents those semantic connections numerically.
So how do we actually create these numerical fingerprints for text?
Well, that's where these powerful models come in. Specifically, models like the Universal Sentence Encoder, often just called USE.
Yugi, okay.
Our source explains that models like USE are designed specifically to turn words or sentences into vectors. You can think of it as giving each piece of text its own unique numerical fingerprint, capturing its essence in a format the machine can understand.
And what makes USC so good at this?
Well, it's based on sophisticated deep learning models, and crucially, it's been trained on vast amounts of text.
So it's seen a lot of language.
An incredible amount. Web pages, books, conversations. This extensive training on really diverse data gives it amazing versatility. It can understand a huge range of topics and sentence structures pretty accurately. It's like a linguist who's studied countless languages and dialects.
And it understands context, too.
That's the key. Its real ingenuity lies in that contextual understanding. It doesn't just look at words in isolation. The source says it looks at each word in a sentence and the words around it to get a full picture of their meaning.
So word order matters.
Absolutely. It pays close attention to word order, grammar, usage, all to grasp the full intent. So a sentence like, the dog bit the man,
Right.
generates a completely different vector from the man bit the dog, even though the words are the same. USE understands that critical difference in meaning conveyed by the structure.
And it's fast.
Once it's trained, yes. USE can convert sentences to vectors incredibly quickly, which makes it highly efficient for real-world stuff.
Okay, let's make this more concrete. The source had a good example, right, about visualizing this.
Yeah, it's a great illustration. Imagine you have two sentences. The latest iPhone is a great camera, and what are the specs of the new Pixel phone?
Right, both about smartphones.
Exactly. After USE processes them into vectors, if you were to use a technique called PCA, which is basically a way to simplify this complex, high-dimensional data so we can visualize it, maybe in 2D or 3D.
Right.
You'd see the points representing those two sentences mapped really close together in the semantic space.
Because conceptually they're similar, even with different brand names.
Precisely. Now contrast that with a sentence like, I love driving my new car.
Totally different topic.
Right, and its vector would be plotted quite far away from those smartphone sentences. This example really shows how this numerical representation lets computers see, quote-unquote, relationships that are obvious to us, but used to be invisible to machines.
It's not just about shared keywords anymore.
No, it's about sharing a similar concept or topic.
Okay, so we have these vectors, these numerical fingerprints of meaning. How do we compare them? How do we know how similar two pieces of text are numerically?
We measure how close their vectors are in space. And this is done using specific mathematical formulas. The most common one, highlighted in our source, is called cosine similarity.
Cosine similarity.
Yeah. It essentially gives you a precise numerical value telling you how similar or different two text fingerprints are. It's basically measuring the angle between the two vectors in that high-dimensional space.
Smaller angle, more similar meaning.
You got it. A smaller angle means greater semantic similarity.
So how does this all come together to actually power search? What are the steps?
It boils down to a pretty clear three-stage process. First, vectorization. When you type your query into the search bar, the engine immediately turns your words into a vector using a model like USE. Your question gets its own unique numerical point in this giant semantic space.
Okay, my question is now a vector. Step 2.
Indexing. The system then scans, very quickly, through a massive pre-built index of other vectors.
And each of those represents
a different piece of information. Could be a document, a web page, maybe an image caption, a product description. Anything that's been turned into a vector beforehand. It's like having this enormous library where every single item has its own conceptual fingerprint already mapped out.
Ready to be found. And step 3.
Retrieval. This is the key part. By intelligently finding the closest matching vectors to your query's vector.
Using that cosine similarity, maybe?
Likely, yes. The engine retrieves information that's not just textually similar, but profoundly semantically related. It's finding documents that discuss the same ideas, explore the same concepts, or answer the same intent as your query.
Wow. That's a huge leap from just finding documents with the same words.
It really is.
This is where it gets really interesting, isn't it? It's almost like the computer is learning to think in concepts, not just letters. This numerical fingerprint for meaning.
Yeah.
It feels genuinely revolutionary.
It allows computers to bridge that huge gap between the fluidity and nuance of our language and the precise computational needs of machines in a way that simple keyword matching just never could.
But that does raise a question, right? How can we be sure these numbers, these vectors, truly capture human intent accurately?
That's a great point. The amazing thing is their ability to generalize. Because they're trained on such vast amounts of diverse data, these models learn to find incredibly subtle connections, patterns we might not even notice ourselves.
So understanding vectors isn't just about search.
Oh, not at all. It's fundamental to understanding so many advanced AI applications. Recommendation systems, language translation, even those generative AI models creating text and images.
They all use this kind of vector representation.
At their core, yes, it's essentially the language of meaning for modern AI.
All right, so we have the Universal Sentence Encoder, USE, giving us this amazing ability to turn language into these meaningful number lists, these vectors. But okay, here's the next big challenge, right?
The scale problem.
Exactly. Once you've got vectors for millions, maybe billions of documents, how on earth do you search through all of that efficiently? Like finding the closest matches in milliseconds.
Yeah, you definitely can't compare your query vector to every single document vector one by one. That exhaustive search would just take forever. It's completely impractical at the scale of modern data.
So we need speed.
We desperately need speed, and that is precisely the challenge that FAISS, that's F-A-I-S-S, Facebook AI Similarity Search, was built to solve.
Okay.
It's the sophisticated answer to that critical need for lightning-fast speed when you're dealing with absolutely massive collections of vectors. Without something like FAISS, all that clever semantic understanding would basically remain theoretical for any large-scale practical use.
So what is FAISS exactly? The source calls it
a library for efficient similarity search. That's its sole purpose, highly optimized, search through huge collections of vectors incredibly fast.
So it doesn't create the vectors.
Yeah.
UC does that part.
Correct. USE creates the meaning vectors. FAISS is the high-speed engine that finds the needle in the haystack after those vectors have been generated.
Gotcha. And what are the main advantages it brings?
Well, several crucial ones for real-world semantic search. First, obviously, efficient searching. It uses these optimized algorithms to rapidly search through large collections of vectors. Speed is its core thing.
Okay.
Second, scalability. It can handle databases of vectors that are just way too large to fit entirely in memory. This makes it perfect for genuine big data applications where you might need to search billions of items in real time.
Wow. Billions. And it's still accurate. Does speed compromise accuracy?
That's the impressive part. It provides highly accurate search results despite the speed. This accuracy comes from its advanced indexing strategies. They're designed to find the right results quickly. It's not just brute force, it's clever, optimized searching.
So how does it do that? How does it achieve that speed and accuracy?
Well, simplifying a bit, the process starts with index building. FAISS intelligently organizes vectors in a way that similar ones are near each other.
Okay, so it's like pre-sorting them conceptually.
Exactly. Think of it less like a chaotic pile of books and more like a meticulously organized library where all the books on, say, physics are already grouped together on the same shelves.
Making it much faster to find relevant stuff than just searching the whole library randomly.
Vastly faster. Then comes the searching phase. When you search with your query vector, FAISS doesn't scan everything. Because of that clever organization, it quickly identifies which part of its index, which shelf in our library analogy, to look at for the closest matches.
So it knows where to focus its effort.
Precisely. It drastically reduces the amount of data it actually needs to examine.
And then retrieves the results.
And finally, retrieving results. Once it zeroes in on that relevant section, It retrieves the most semantically similar vectors, which of course correspond to the most relevant search results for your query. It's an incredibly optimized lookup.
Now, you mentioned indexing strategies. Is there just one way FAISS organizes things?
Oh no, it's quite flexible. It's not one size fits all. Our source mentions that for simpler or smaller data sets, something called index flat L2 might be fine.
Index flat L2. What's that?
It basically does an exhaustive search. It literally compares your query vector to every single other vector. Super accurate because it checks everything.
But slow for big data sets.
Exactly. It becomes prohibitively slow when you scale up.
So for bigger stuff.
For larger data sets or more advanced applications, FAISS offers more sophisticated indexes. The source mentions things like index IVF flat or index AVFPQ.
IVF flat. IVFPQ.
Okay? These are clever techniques that give you much faster search times and reduced memory usage. They achieve this by making a tiny calculated trade-off. They might sacrifice an almost imperceptible amount of absolute accuracy.
For huge gains in speed.
Massive gains. For example, index IVF flat might partition the whole vector space into maybe, say, 100 conceptual cells. When you search, instead of checking all 100 cells, it might only check the 10 cells closest to your query.
Like narrowing down the search area dramatically.
Precisely. There are parameters like nlist and nprobe mentioned in the source that let developers fine-tune this balance between speed and precision for their specific needs.
So putting it all together, USE understands the language, turns it into vectors.
And FAISS lets us search through those vectors incredibly quickly to find meaningful connections.
They're a powerful duo.
Absolutely. The source says combining them creates a semantic search engine that's both smart and swift, which is crucial, right? It's not enough just to be smart. You need to be fast and scalable to be practical.
It really is like having that perfect map for a giant city. USC gives us the precise addresses, the semantic locations.
And FAISS provides the super fast navigation routes to find them, no matter how huge the city is.
Yeah, without FAISS, even with all those clever vectors telling us where everything is conceptually, we'd just be lost wading through data. It's the piece that makes semantic search actually work at scale.
And it forces that important engineering question. What are the right trade-offs between pure accuracy and raw speed for a given system? FAISS is great because it offers that spectrum of indexing options developers can choose.
It really shows that advanced AI isn't just about the algorithms, is it?
Not at all. It's also about the incredible, often invisible engineering needed to make that intelligence practical and performant for millions or billions of users. And this tech is working behind the scenes in many of the smart instant search results you get every day.
Okay, so we've covered the concepts, the vectors with USE, the speed with FAISS. Now let's actually bring it all together. Let's see how you build a real working semantic search engine using that example from the source. The 20 newsgroups dataset.
Right, the 20 newsgroups. It's a classic data set. It's basically a collection of old email posts from 20 different newsgroup categories.
Newsgroups, like early internet forums.
Exactly like that. Think Reddit, but way back when. And the topics are super diverse. The source lists some. alt.atheism, comp.graphics, rec.auto, sci.space, talk.politics.guns, soc.religion.christian, all sorts of things.
So real conversations.
Real, often messy, human conversations from the early internet.
And that's why it's good for testing semantic search, because it's messy.
Partly, yes. First, it's full of natural language, actual discussions with all the slang, the informal phrasing, the typos, all the nuances of human language.
It's a tough test.
Definitely more challenging than perfectly clean text. And second, there's a huge prevalence of context. The conversations really require an understanding of context to differentiate between the topics effectively.
So keywords alone would fail often.
Very often. Think about a word like drive. Could be about cars, could be about computers, could be psychological. The data set forces the system to grasp meaning, not just spot words.
Okay, so what's the overall process for building the search engine with this data set?
Our source lays out 4 main steps. First, exploring data, just loading it up, understanding the structure. Pre-processing, this is crucial. Cleaning up that raw text, removing unwanted noise.
We'll come back to that. Step 3?
Vectorization. Using USE to turn the cleaned text into those numerical vectors.
And finally,
Semantic search implementation, using FAISS to index the vectors and actually perform the searches.
okay, let's focus on that pre-processing step. You said it's critical.
Absolutely. The source puts it well. Pre-processing is a critical step to ensure the quality and consistency of the data before it's fed into the universal sentence encoder. Raw data, especially from conversations like these news groups, is inherently messy.
Like how?
Oh, you get tons of email headers, long signatures, maybe quoted text from previous replies, weird formatting, random punctuation, stuff that's part of the communication but doesn't really add to the core semantic content we want the model to learn.
Right. This is the dirty work of AI, isn't it? But
No,
essential.
totally essential. It's like prepping ingredients before cooking. You wouldn't just throw everything, packaging and all, into the pot.
Oh, good point. So the source has this pre-processed text function to do the cleaning.
Yes, exactly. And it walks through a great example using one specific post from the dataset sample index equals 0, which happens to be about a quirky car called a Bricklin.
A Bricklin. Okay. What did the original post look like?
Oh, it's a perfect example of raw data. Let me read a snippet of the start.
Lurkexed it at wham.mmd.edu. Where's my thing?
What car is this?
rec3.wham.mmd.edu.
University of Maryland College Park.
15. I was wondering if anyone out there could enlighten me on this car I saw.
Okay, yeah, very cluttered. Headers, email addresses.
Exactly. So the first thing the preprocessed text function does is removing email headers. It strips out lines starting with from, subject, organization, lines, etc. That's metadata, not the actual content.
Cleans it up right away. What's next?
Eliminating email addresses. Patterns like lurkest at wham.umd.edu get removed. They're specific identifiers, not general meaning. Makes sense. Stripping punctuations and numbers. This is the big one. It keeps only alphabetic characters. So exclamation points, commas, periods, numbers, all gone. That bit, it was a two-door sports car. Late 60s, early 70s, becomes more like it was a door sports car. Late early.
Wow, simplifies it a lot.
It does. Then converting to lowercase. Crucial for consistency. What car and what car become the same. Everything goes lowercase.
Prevents the model thinking capitalization means something different.
Precisely. And finally, trimming excess white space. Cleans up extra spaces, tabs, line breaks, everything gets condensed neatly.
So after all that, what does the Bricklin post look like?
The source shows the final pre-processed text. It's basically just a long string of lowercase words like, the subject folk, what car is this? NNT posting Ghost Rock Wam to do organization, University of Maryland College Park Lines. I was wondering if anyone out there could enlighten me on this car. I saw the other day it was a door sports car. Looked to be from the late early. It was called Bricklin. The doors were really small, and so on.
Much cleaner. Standardized. Ready for the next step.
Exactly. The source emphasizes, by pre-processing the text data, we reduce noise and standardize the text, which is essential for achieving meaningful semantic analysis. If you feed noisy, inconsistent data into USE,
Garbage in, garbage out.
pretty much, the vectors won't accurately capture the meaning. This detailed cleaning ensures USE gets the clearest possible signal to work with. It really highlights how much effort goes into data prep in AI. It's not glamorous, but it's often the difference between success and failure.
All right, so we've cleaned the data meticulously. We've used the universal sentence encoder to turn that clean text into meaningful vectors. Now, the payoff. Bringing in FAISS to actually do the semantic searching, this is where we see it all work.
Right. So typically you'd create a search function. This function takes your query, the question you're asking, and maybe how many top results you want back, like the top 5 or top 10.
Okay. And inside that function,
It follows a sequence. First, your query itself gets pre-processed using that exact same pre-processed text function. Consistency is key.
so the question gets cleaned just like the documents were.
Exactly. Then, that cleaned query is turned into its own vector using the embed text function, which uses USE. Your question is now a numerical fingerprint,
Ready to be compared.
ready to be compared, and that's the core step. It searches with FAISS. The function feeds your query vector into the FAISS index. FAISS then does its magic, rapidly finding the nearest neighbors, the closest vectors in that semantic space.
And it returns.
Two main things. The distances, that numerical score showing how close each match is semantically, and the indices, which tell you exactly which documents in the dataset correspond to those close vectors.
And the amazing part here is that the results are based on semantic understanding, right? Not just keywords.
Absolutely. It's all about contextual relevance, conceptual similarity. Let's look at those examples from the source again because they really drive this home.
Okay, like the first one, space exploration.
Right. A traditional search might just look for that exact phrase.
Yeah.
But our semantic engine understands the concept. It would find documents talking about rockets, planets, NASA missions, astronauts.
Even if they don't use the exact words space exploration.
Correct. Because the meaning is related. It grasps the theme.
What about computer graphics and algorithms?
Same idea. A keyword search might need both terms. The semantic engine would find posts about rendering, visual effects software, computational geometry, image processing, related concepts within that technical domain.
Okay, now the really interesting one. Discussions on religion and atheism. What did the source show for that?
This was a great example. The second-ranked result had a very close semantic distance, like 1.07, and the snippet from the original post it returned was fascinating. It included lines like, there are two issues here, religion and religion. Religion is personal belief system. Religion is a mimetic virus. I don't have any problem with the discussion of religion. It's just religion that I can't stand.
Wow. So the actual query phrase, discussions on religion and atheism, isn't even in that text.
Not literally, no. But the document is clearly deeply engaged with the concept of religion, even making distinctions within the term. The semantic engine correctly saw that profound relevance based on meaning, not word matching.
That's incredible. It really understood the nuance.
It did. And the third result, slightly further away semantically, had the subject line, Re-Atheism Survey. Again, no exact match on the query phrase.
But clearly relevant conceptually.
Unmistakably relevant. These examples perfectly show that getting the gist and making connections, capability. The system understands the intent behind your query.
What about a more everyday query, like the best car for a student?
Again, it wouldn't just look for best car student. It understands the context. A student probably needs something affordable, reliable, maybe fuel efficient. So it would find documents discussing those aspects, even if they don't use the exact query words. It gets the underlying need.
And when it shows you the results, you'd see the ranking, the distance score, and the actual text.
Exactly. You see the ranking, how close it is, the distance value, the numerical similarity, and the actual document text. So you can immediately see why it was considered a good match. It's transparent.
This really is the payoff, isn't it?
Yeah.
You type in a natural question, and the engine just gets it. It's amazing to see how those vectors and FAISS come together to pull out what you meant, even if your wording wasn't perfect.
That's a fundamental shift. And it leads you to wonder, right, how do we keep refining this? How does it get even better?
Yeah, what's next?
Well, the continuous development of even better embedding model successors to USE and even more efficient indexing techniques within tools like FAISS, it means semantic search is just going to become more intuitive, more precise, more powerful over time.
It feels like a genuine breakthrough for finding information, especially with complex topics or just wading through the sheer amount of data out there.
Absolutely. Think about legal discovery, scientific research, even just organizing your own massive digital archive. Semantic search offers a real solution to information overload. The future of finding information is definitely semantic.
Wow, what an incredible deep dive that was. We really covered a lot of ground. We started with that common frustration, didn't we? Traditional keyword search, just not quite getting what you mean.
That feeling of the search engine just not understanding your intent, yeah.
And then we jumped into the, well, kind of abstract but really powerful world of vectors, those lists of numbers that somehow capture the meaning of words and sentences, giving everything its own unique numerical fingerprint.
And the ingenuity of the Universal Sentence Encoder, UAE, turning our messy human language into those precise vectors, understanding context and nuance along the way.
Then discovering the sheer speed and scalability of FAISS, that similarity search library, making it possible to sift through billions of those vectors almost instantly, finding the relevant information super fast.
Which is critical for making it practical.
Absolutely. And finally, seeing it all come together with that 20 newsgroups example, going through the vital, if sometimes tedious step of pre-processing that messy, real-world data.
Cleaning it up so the AI can actually understand it properly.
And then watching it work, seeing how a query like discussions on religion and atheism pulled back results that were conceptually spot on, even without the exact keywords being there.
It really drives home that semantic search is so much more than just a tech upgrade. It feels like a fundamental shift in how we interact with information, how we discover things.
Yeah, it brings us so much closer to that future where machines don't just process our words, but genuinely understand our language, our intent, moving beyond just matching patterns to actual comprehension.
It's not just an incremental improvement. It feels like a revolution in how we connect with knowledge. It promises to make our digital interactions more efficient, definitely more insightful, and hopefully a lot less frustrating.
So if we think about the really big picture here,
Well, this ability for machines to grasp nuance, to understand meaning through semantic search, it really moves us closer to systems that don't just handle data, but genuinely augment human intelligence, extend our own capabilities.
which opens up some pretty big questions, doesn't it?
It really does. As AI gains this deeper understanding of meaning, What new frontiers of knowledge might we unlock? What entirely new possibilities for creativity, for discovery emerge when we can interact with information in this much more intuitive way, going far beyond just finding things?
Yeah, how might this fundamentally change how we deal with everything from our own personal notes to the entire web if the systems truly understand?
It's definitely something to think about. What new questions will you ask your smarter search engine now?